Hello, this will be a demonstration of proposition 5 from book 6 of Euclid's Elements, which says that if two triangles have their sides proportional, the angles about the proportional sides will be equal to one another. Not only is this another similarity theorem like the previous proposition, it is the total converse of the previous proposition. So instead of being given that the two triangles are equiangular and from there proving that the sides about the equal angles are proportional, we're given that the sides of the triangle are proportional, and then from that we're going to prove that they are equiangular. What that's going to look like is we're going to have the two triangles A, B, C. Look something like that, let's say. A, B, C. And we're also going to have D, E, F, like that. Okay. And we're going to have these two triangles such that their sides are proportional. What that means is that AB is going to be to BC, just as DE is to EF, and also that BC is to CA, just as EF is to FD, and finally that BA is to AC, just as ED is to DF. And what we're going to prove from there is that these two triangles are equiangular, specifically that the angles contained by the proportional sides are going to be equal. That's going to mean that we're going to show that the angle ABC is equal to the angle DEF, that the angle BCA is equal to the angle EFD, and finally that the angle BAC is equal to the angle EDF. We're going to begin by constructing on the straight line EF and at the points E and F respectively, the angles FEG and EFG such that they are equal to ABC and ACB respectively. So give me one moment to do that. At E, we're going to make the angle FEG equal to the angle ABC, like that. And we're also going to make the angle at point F, the angle EFG equal to the angle ACB. Like that. And because these two triangles ABC and EFG have two angles which are equal to two angles, we can say by proposition 132 and common notion 3 that the third angle will be equal to the third angle. This is something that I explained at the end of my video on proposition 6.4, that if you know two triangles have two angles equal to two angles, then the third angle is equal to the third angle. Okay, so these two triangles, ABC and EFG, are equiangular, which means by proposition 6.4, the sides about the equal angles are going to be proportional. So that's going to mean that for example, AB is to BC just as GE is to EF, right? So AB and BC contain the angle ABC, which is equal to the angle FEG contained by FE and EG, which means that that AB is to BC just as GE is to EF. But we were also given that AB is to BC just as DE is to EF, which means by proposition 5.11, we have two ratios which are the same with the same ratio, which means they are the same with one another. So we can say that DE is to EF just as GE is to EF, but by proposition 5.9, magnitudes which have the same ratio to the same are equal, which means that DE is going to be equal to GE. We can prove in a similar manner that DF is equal to FG. That would involve saying that, because the two triangles ABC and EFG have been proven similar by 6.4, then AC is going to be to CB, just as, GF is to FE. But again, we were given that AC is to BC, just as FD is to EF, which means that FD is to EF, just as GF is to FE, which means that GF and FD are equal to one another. Okay. So we have these two triangles, DEF and GEF, which have two sides equal to two sides, and a third side which is common to both, which means by proposition 1-8, the side-side-side congruency theorem, these two triangles, DEF and EFG, are equal in all respects, namely that they are equiangular. So the angle FEG is going to be equal to the angle DEF. The angle EFG is going to be equal to the angle DFE. And finally, that the angle EGF is going to be equal to the angle EDF. Makes sense. But we know, because of how we constructed the triangle EFG, that the angle ABC is equal to the angle FEG, which means that because the angle DEF is also equal to the angle FEG, by common notion 1, we can say that the angle ABC is equal to the angle DEF. Now, in a similar way, we can easily demonstrate that the angle AGB is equal to the angle DFE, and finally that the angle BAC is equal to the angle EDF. And this is all that we set out to prove. We set out to prove that given that the sides of these two triangles ABC and DEF are proportional, they will be equiangular, namely that the angles contained by proportional sides will be equal. And we've just shown that the angle ABC is equal to the angle DEF, that the angle ACB is equal to the angle DFE, and finally that the angle BAC is equal to the angle EDF. Having proven that the triangles are equilateral, we are done with the proposition, therefore, etc. QED. Now, I said at the beginning, this is the total converse of the previous proposition. So instead of being given that the triangles are equiangular, we're given that the sides are proportional, which means that this is going to be the side-side-side similarity theorem. Not the congruency theorem like 1-8, but the similarity theorem. All the similarity theorems are going to be very important to remember, especially the first three. 6-4, 6-5, and the upcoming 6-6 are very important. They come up a lot. 6-7 is true, but it's not as common within the elements. You also don't see it as much in modern geometry, but it's nonetheless true. So remember your similarity theorems. You should remember them like you remember your congruency theorems from book 1. Again, this is the side-side-side similarity theorem. Which again is the total converse of the angle-angle similarity theorem. Having nothing more to say about this proposition, I will end the video here and move on to 6-6.